All right, so let's go ahead and get started. So I haven't had an opportunity to talk to you face to face about exam performance, so I wanted to talk a little bit about that. So the average you can see was 83, median was 85, half the class is getting a solid B or better at this point in time. And then I also wanted to let you know, I think that's a really good job. You're up 5 or 6 points from last semester taking the same exam. And then I had a little bit more extra credit padding last time. So this time there's 1 point extra credit. So last time it was probably 3 points. So at any rate, this means that you guys have definitely done better. So kudos. I also wanted to make sure that everybody realizes, because the course is hierarchical, what happens is exam performance doesn't stay at this high level in general. I'd like you to prove that statement wrong, but in general, exam 2 is a little lower than exam 1, and then exam 3 is a little bit lower as well. All right, so that means keep working, keep doing what you're doing, and amp it up a little bit. Did want to talk a little bit about folks that are in this region, so mid 60s to low 70s. I'd like to see you modify your, whatever you're doing to prep for the class. You want to amp it up a little bit, bring it up with the rest of the group. Those of you in this region, I'd like you to meet with me. We should talk because you need a major overhaul in your approach to the course. Okay? All right, any questions about the exam? All right, so if you didn't get a chance to pick it up, you can stop by office hours and look it over, and that's when you can request regrades. And there's a hard deadline, I think, of next Tuesday for the regrade requests. Okay, so I also wasn't here on Monday. Did anybody notice? All right, so I posted lecture notes, or I posted the captured lecture. Hopefully it worked out well enough that today we'll follow on it nicely. All right, okay, so some things that I want to just talk about at the outset. So we've introduced this system partition function. And the definition of the system partition function is it's the summation of the Boltzmann factors, and the Boltzmann factors have the energies of the systems in our ensemble. All right? Does that make sense? All right, so that's our clear definition of system partition function. We've also introduced a molecular partition function. That's the small q. It again consists of the Boltzmann factors, but now the energies refer to the energies that the individual particles have. All right? And what we know, we've shown that we can use the system partition function. We can manipulate that using statistics and some math tricks and get an expression for average energy or any thermodynamic property. Well, because the Boltzmann factor has the same form for the particle or the molecular partition function, those same things that we've previously derived will hold true. I can calculate the average energy of an individual particle using the partition function. Okay? So that's going to carry forward. All right, and then the last time that we met for lecture that I was here was on Wednesday. At that point, we showed that if we have distinguishable particles, the system partition function consists of the product of the particle or the molecular partition functions. All right, and if those are identical, then we expect each of those partition functions to be the same. So if I had only xenon, this would be the partition functions for xenon. Same partition function, just a different particle. So that means that I have q to the n. Right? We pointed out that distinguishable is sort of limited because if I have something in the liquid phase or in the gas phase, you can't distinguish one molecule from another molecule. So they're indistinguishable. So the only case that this applies to and what we've talked about is the solid state. Because in the solid state, things are distinguishable by where they sit. Right? Does that make sense, everybody? Okay, and then in the lecture that I've posted online, hopefully we've talked about, hopefully this comes across clearly, but we can't use this same relationship as it is. And there's two reasons for it that are fundamental. One, you may recall back from general chemistry, the Pauli exclusion principle. Who remembers Pauli exclusion principle. That says that you can't have two electrons in an atom with the same set of quantum numbers. The other way that you can word that is you can't have two electrons in the same atom in the same quantum state, right? Because the quantum numbers define the state, right? Now, it turns out that there's more than just electrons, so fermions in general can't have two particles in the quantum state. So we have to worry about that. The other thing that's a consequence of quantum mechanics is that if I have, say, a system of two particles in two levels, if particle A is in the upper level and B is in the lower level, that is indistinguishable from the reverse of that, all right? And that means that there's only one state, all right? So instead of there being what we would think of macroscopically as two states, there's only one fundamental state. And that tells us that this Q to the n will overcount the number of states by that transposition. I may have made up a word there, but hopefully it makes sense. I'll have to look it up after class. All right, so then we say, how do we deal with this? Well, the one thing that we can say is that if we know that there's a lot more quantum states available than there are particles, then we can say it's really unlikely that two particles are in the same quantum state, right? And that's going to hold true for ideal gases, all right? And we defined what our criteria for determining that is, right? The other thing that we showed in the lecture was that we can take care of that overcount by n factorial, right? So the number of particles factorial tells me the number of ways of arranging x objects into x slots, all right? Does that make sense? Okay? All right, so we've established that for our independent, indistinguishable atoms or molecules, we're going to be able to use this relationship relating the system partition function with the particle partition function. All right? Then we can formally define the particle partition function as the sum of the Boltzmann factors. All right? And then what we've shown previously is that because of the way the Boltzmann factor works, the probability of a molecule being in a particular quantum state can be determined by the Boltzmann factor that corresponds to that state over the partition function, right? So we can get the same probabilities. And the energies of that particle will be the energy times the Boltzmann factor over Q, because that's the summation, or the average energy will be the summation of the energy times the Boltzmann factor summed over all of the possible states. Right? And then we've previously shown that that's the same as kBt squared, partial derivative of natural log of Q with respect to t. Right? So those all those things that we previously have shown will hold true for our system, for our particle partition functions. All right. The other thing that was shown, and you'll be asked explicitly in homework 7 to show this, is that the partition function for the particle can be broken up into the various modes of energy. So I can use it's basically going to be the product of the translational partition function, the rotational, vibrational, and the electronic partition functions. All right. So again, we can define the probabilities, and then we can talk about the average energy. And those probabilities and the average energy will be according to particular modes. So I can ask, what's the probability of being in this translational energy level? Or what's the probability of being in this vibrational level separate from the rest of the modes of energy? And because I can separate the probabilities, I can separate out the average energy. So I can calculate for a particle the translational energy, the rotational energy, the vibrational energy on average. Right? Okay, and then the last thing that was covered in the lecture that's posted is we've been talking about the molecular or particle partition function in terms of quantum states. So we summed Boltzmann factors over all of the quantum states that are available. We know that sometimes we have what we call energy levels, where we have more than one quantum state there that has the same energy. That's degeneracy. Well, I can use energy levels to determine the partition function. So the only difference is whenever I'm talking about the energy, in this case it's an energy level, and I need to include in this the degeneracy of that particular level. Make sense? Okay, the other thing that I just wanted to mention at the outset here is, let's say that I have the average energy of one of the modes of energy. So it could be translational, rotational, vibrational. If I have a system that has all the same particles, what do I need to do to that in order to get the system average energy? So let's say that I have a mole of argon, right? I know the average energy of one argon molecule. How do I get the system energy? Thank you. Thank you. First, so because I'm not feeling that well today, I was going to share the pain. I'm passing the box around. Everyone gets sugar. So if I get really boring today, at least you'll have a sugar high for a moment. Actually, what I should do is have everybody grab a piece of candy. If somebody falls asleep, everybody throw their candy at that person. Sorry. Don't do that. I will get fired. All right, so I can multiply by the number of particles to give me the average system energy for that particular mode. All right, and I will work on making sure that my handwriting is better today. Okay, so from here, what we're going to do is we're going to review a little bit of that. We're going to have a quiz. And then we're going to move into Math Chapter C, where we're going to talk about the Maclaurin series. How many people have heard of Maclaurin series before? So this is a review for some. Who's it new to? A few of you? All right, well, hopefully it'll make sense. So whenever we make a Maclaurin series, we have a function and we're creating a series that is the same as that function. We need to show that it works, and that means that it needs to converge. If you think about the one that we've used, the exponential function, e to the x, if I put a value in for x, we know that's a single number. That means that my series that describes that has to converge on that single number. Right? So we have to test the series for convergence. Right? And then from there, what we're going to do is show where the partition function for translation comes from. And over the next few lectures, we're just going to be talking about where the particle partition functions that we've been using come from and deriving them. All right. So I think where we'll get to today is the translational partition function. We might have a moment to talk about the electronic partition function. The rest of it will move forward. All right. Okay, so again, I just wanted to take a moment to look at this slide. So for this slide, what we see is that we've got the partition function for our particle. It's the product of the partition function for translation, rotation, vibration. And that allows us to tease out translational probabilities, rotational, vibrational, electronic. And of course, if I can tease those out, I can get the energy of those modes. Okay? All right, so a direct application of this will be done by you in this quiz. All right, this is a group quiz. You can work with up to 4 people. Right? Are you guys a group of 3? If you don't want to be, that's fine. Okay, and only work on the page that says names. All right, that's probably enough. If you could pass one behind you. Are you guys going to group up at all? I've got one more. Just I'll hand them out. You guys spread them wherever you want to spread them. Okay? Does everybody have a quiz that needs a quiz?
finding this? Are we doing like the same thing that we did before?
So I'm asking you to determine the energy of rotation for the system. And I've given you the particle partition function.
There is no T in it. So then we define a natural log of the derivative of the natural log of this.
Because you can break it apart into elements.
Natural laws of this, like natural laws of all the terms that plus all the terms that
You can say LMC plus LMC.
I don't like weird details. There's too many like weird symbols. I was like fine with these before, not with making sense.
Well, the P is just saying that P is constant. It's not like multiplying by.
yeah, whatever is put underneath there.
I thought that's what it was originally, and then you said it was times U. And I was like, oh, okay. So this whole thing is times.
All right, why don't we talk this one? How many people think they're done? How many would like a few more minutes? All right.
That's it. Oh yeah, because that's what you wrote. Why are we finding this? We need a molar. So wouldn't that just be times?
All right, let's go ahead and talk this one through. All right, so I've given you a molecular partition function. It's broken up into the translational, rotational, and vibrational. Because I'm interested only in the average rotational energy, then I'm going to focus on the rotational partition function. So I have kBt squared, partial natural log of the partition function with respect to t. So I go back to my rotational partition function. Because I'm going to take the derivative with respect to t, I want to put that in terms of t. And because I know that I'm going to take the natural log and then the derivative with respect to t, I separate it out according to the terms that are important. So t only shows up one place, so I have natural log of t plus the natural log of everything else. So that I can plug in for natural log of the partition function. So I take the derivative of the natural log of t, that gives me the reciprocal of the temperature, and then the derivative of the natural log of the rest of it doesn't have t in it, goes to 0. So I'm left with kBt. All right? Now that's the rotational energy that's an average value for a particle. In order to get the system energy, I multiply it by the number of particles. And if I'm talking about specifically 1 mole, that means the number of particles is Avogadro's number. I have Na kBt, which is the same as RT. Okay? Make sense? All right, moving forward. So we're going to start talking about series and a little bit about some limits. Okay, so I'll collect it later. Yes, you will turn it in. All right, so we have the exponential function that we've previously stated can be written as a series. So we're going to show where that comes from. All right. So what we can do is we can say, let's assume that our function can be written as a series expansion. So that's what I've got. F of x, we're letting it be written as a function of a polynomial of x. All right? That means that we need to determine what these values of c are. All right? So the first one's pretty straightforward. I set x equal to 0. F of 0 will then be the same as C0, thank you. Okay? All right, so that means I've got the first term. So if we're talking about the exponential function, this will be e to the 0, which is 1. Right? Make sense? Okay, so next up, what we can do is we can say, well, I want to determine the rest of them. So I'm going to take the derivative of the function with respect to x. Well, that first term's going to go away, so I'm left with c1. That's what's left after taking the derivative with respect to x. The next term will be, help me out, what's the next term? 2c2x, and then the next one will be 3c3x squared. Okay? All right. And then what we can do is say, well, I can get c1 by evaluating this derivative at x equals 0. Okay? So, and the way that we indicate that, we say df dx at x equals 0 is the same as c1. Okay? c2, that's the next thing that we'll try to get to. We take the next derivative. All right? So then I'm going to end up with, what's my first term? 2c2. And my next term will be 3 times 6, or 3 times 2x plus dot, dot, dot. Okay? Make sense? Now, if I evaluate that at 0, so d second derivative at x equals 0, that's going to be 2 times c2. Okay? Now, because what we're interested in is c2, I need to rearrange this. So I can say c2 is equal to 1 over 2 times the second derivative with respect to x evaluated at x equals 0. Okay? All right, and then you probably see where this is going. I take the third derivative. That gets to be 3 times 2 times c3. All right? So because we know that what we're interested in is c3, I'm going to say c3 is equal to, it's clear that it's related to the third derivative evaluated at x equals 0. And what do I need to have in front of it? 1/6, right? Or 1 over 3 times 2, right? Make sense? Okay, so the other thing I just want to point out here is that this is 3 factorial, right? This is 2 factorial, and the previous one is 1 factorial. So we can generalize and say that the nth value of c is given by 1 over n factorial times the nth derivative evaluated at x equals 0. Okay? All right. And so what we've done is we've established a way to create a series that corresponds to our function, right? And this is what's called the Maclaurin series. All right, so let's go ahead and do that for our function e to the x. So what's the nth derivative of e to the x? It's e to the x. All right, and then the nth derivative of e to the x evaluated at x equals 0 will be e to the 0, which is 1, right? Okay, so that basically says for the exponential function, this term and this term and this term and this term, those all go to 1. So the only thing I need to include in here are the factorials and the x's. 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Okay? Make sense? All right, and as I said at the outset, if I put a specific value in for x, I expect to get a single number out. So that means that this series has to converge on a single number. The test for the convergence is called the ratio test. And it basically looks at the n plus 1 term compared to the nth term. And it's a lot easier to apply it than it is to explain it. So let's just go ahead and apply it. All right. So for this example, we're going to say limit as n approaches infinity. All right, so we're going to go to the n plus 1 term in the numerator. So that'll be 1 over n plus 1 factorial times x to the n plus 1. All right, and then the nth term will be 1 over n factorial times x to the n. All right, so we want to simplify this a little bit. So I'm going to put the limit, n approaches infinity, absolute value. All right, so I've got the reciprocal of n factorial below. That's going to put it in the numerator. So this becomes n factorial over n plus 1 factorial. And then what happens to my x term? X to the n plus 1 divided by x to the n gives me x. All right. You guys did so much better at that answer than my 10 o'clock class. I can't believe I'm recording this. 10 o'clock class, pay no attention to what I just said. You guys are good. Love you. All right. All right. Oh, it's so much better to live without the S word. All right. I didn't break the seal. That's the S word. Okay. So anyways, let me just look at this a little bit closer. So if we think about n plus 1 factorial, right, that means it's going to be n plus 1 times, what's the next value? N, and then n minus 1, and n. So that really means this is n plus 1 times n factorial. We agree? All right, so n plus 1 factorial equals n factorial times n plus 1. All right, and so that means that that whole term can be replaced with, I'll just rewrite all of it here. So this will be the limit n approaches infinity of x over n plus 1. All right, and as n goes to infinity, what happens to this? It goes to, the bottom goes to infinity, which means the totality goes to, right? And is 0 less than 1? It is. I think so too. All right. All right, so what we've shown then is that this series works. It converges for all x's. Okay? So there's no restrictions on it. This series works. Okay? All right, so let's look at another example just to make sure that we see what happens when it maybe doesn't work all the time. All right, so we're not going to derive this series, but it's pretty straightforward. This is called the geometric series, 1 over 1 minus x. That's the same as 1 plus x squared plus x cubed, etc. Okay? All right, and you can demonstrate this using the Maclaurin series. Quite straightforward. All right, so we want to test it for convergence. So this is going to be the limit as n approaches infinity. My n plus 1 value will be x to the n plus 1. And then I'm comparing that with the nth value, so x to the n, right? And that's going to become the limit as n approaches infinity of the absolute value of x, right? Now we need this to be less than 1. So what restriction do we have on x? x has to be less than 1, right? Make sense? Okay, so that tells us the series converges only if x is less than 1. All right, and that's pretty important because that tells you when you can't and can use this series as equivalent to that function. Okay? Make sense? All right, so I did want to take a moment to just show you, this is a little math trick that I think is sort of nice to see. There's another way to get at this same series. So this is a derivation of the geometric series. So we're basically going to say, let's have a series. We're going to make it 1 plus x squared plus x cubed. All right? And then I can take that series and multiply it by x. All right? So that's what I've done below. So I have x plus x squared plus x cubed. All right? Then I can take the difference between the two of those. All right? And if you look at this carefully, you see that this is going to be the series times 1 minus x. All right? And then we look at what the difference is. So I see that x is going to cancel, x squared is going to cancel, x cubed is going to cancel. What's not going to cancel? 1's not going to cancel, and x to the n plus 1. All right? So then what I can do is I can rearrange and say that this series is the same as 1 minus x to the n plus 1 over 1 minus x. Okay? All right? And if we add the restriction that x has to be less than 1, as n gets really, really large, what happens to x to the n? If x is less than 1, the square is going to be smaller, the cube is going to be smaller, right? So as n approaches infinity, what happens to this value? It goes to 0, right? Okay? Make sense? All right. I also like showing this because this is a nice visualization of the Maclaurin series. So you can work through the Maclaurin series that we've derived. Sine of x is equal to x minus those extra terms, right? Well, this is the sine of x. That's the function that we're asking for the equivalency of. If we include only the first term, sine of x equals x, that's a line. That represents this red thing, right? And we see that that's only going to work in a small region. If I want a better approximation, I include the next term. And what we clearly can see is as I add more and more terms, I get closer and closer to the original function that I'm interested in. Make sense? Okay. All right, so next thing we're going to talk a little bit about limits and how series can help us with them. All right. So if I went to do the limit as x approaches 0 of sine of x over x, I'd say, oh, I'll put sine of 0 in there over 0. And then you say, what's sine of 0 over 0? It's undefined, right? So when you've run into those situations previously, I'm sure it happens on a day-to-day basis for you, right? You say, oh, okay, L'Hopital's rule, right? The limit of a ratio of functions is the same as the limit as x approaches n of, help me out, f prime over g prime. All right, so for this particular example, that's going to be the limit as x approaches 0 of, what's the derivative of the sine of x with respect to x? Cosine of x. All right, and the derivative of x with respect to x is 1, and that means that our answer is cosine of 0, which is equal to 1. Okay? All right. So this is one way to do it. We also could do it using the Maclaurin series, right? So here I've got the Maclaurin series. Here's sine of x, function of a series of x, right? Because I'm interested in knowing the limit of sine of x over x, I can say 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus etc. Okay? All right, so this is the function that we're interested in knowing the limit as x approaches 0. And we can see that it's very straightforward that if I plug 0 into that series, it's going to end at 0, 0, 0, 0, 0. So I'm left with 1. All right. Okay? All right, next up, we're going to move into chapter 4, and basically what we want to do in this section, or in this chapter, is to derive molecular or particle partition functions. Which is q, little q, which is a function of v, and beta, which we know is 1 over kBt, so it's also a function of temperature. All right? Because we're primarily going to be interested in gases, we're going to be limiting ourselves to ideal gases. All right, and our goal, all right, so stepping back a little bit, we know that we can always write the expression for a partition function as a series, right? But we also know that series aren't easy to deal with, right? And we know that we can take the derivative of the natural log of our partition function with respect to t and get energies. I can take the derivative with respect of that same natural log of the partition function with respect to v, and I can get pressures, right? And so what I want is an easy-to-use analytic expression. So derive a mathematically easy analytic expression for Q. Okay? All right. Okay, so just a couple reminders. We know the relationship between the system partition function and the molecular partition function. And in order to use this relationship, we need to limit our discussion to independent, indistinguishable, and indistinguishable, and for this one, identical particles. Right? So this equation is limiting us because ideal gases are independent and indistinguishable. All right. And we've pointed out that this is going to work for what we're interested in for ideal gases, because we know that we're operating with low pressures and small n over v's, right? Which was our criteria for using this equation. Okay, that guarantees that each of our particles are in a unique quantum state. All right. Also in this chapter, we're going to calculate heat capacities of ideal gases. All right, and we're going to see that that's going to be important whenever we move into chapter 5, talking about properties of gases and work and expansion and that kind of stuff. Okay? All right, so what we're going to start with is looking at the partition function for a monoatomic ideal gas. All right, so we're going to start, by talking about energy levels, right? And we know from chapter 1 that to describe the energy of monoatomic ideal gas, I need to think about translational energies and electronic energies, and that's it. And then what we showed in chapter 3 is that the molecular partition function in its totality is going to be the partition function of translation times the electronic partition function. All right? And so what we're going to do is we're going to introduce each of these independently of each other. Right? We're going to start with the translational partition function. Okay? All right, so coming back to chapter 1, we said that from the particle in the box, we could write the energy levels that are permissible to a particle. Right? And that's going to be h squared over 8ma squared times nx and y and z. Squared, squared, squared. All right? And again, these are our translational quantum numbers, one for the x direction, one for y direction, one for the z direction. And they span from n equals 1 to infinity. Let me just write that. N sub I from 1 to infinity. Okay? All right, so that tells us what's permissible to our particles. All right? So our partition function is going to be the summation of the Boltzmann factors. All right? And if we think about it, I've got to sum over nx, ny, and nz. All right? Because I have to sum over all the indices. It's all available energy levels. So summation nx equals 1 to infinity. Summation ny equals 1 to infinity. And z equals 1 to infinity. Okay? All right. And we now know that we're going to put in the Boltzmann factor. All right? Now, because I have these energy levels, right, in general, the Boltzmann factor is the exponential of minus beta times the energy. All right? That's a lot of stuff to write, so I'm going to write exp to mean the exponential function. All right? And then I've got minus beta. All right? I think what I'm going to do here is I'm going to do some substitution. All right? Because everybody's going to be multiplied by this value. All right? So I'm just going to give it, give me a letter. What letter do you want to use? Anything but Q. W. We'll use W. All right. Now we're going to see W down the road we're going to use, so I'm going to put little wings on it. So that's a winged W. All right, so minus W times nx squared plus ny squared plus nz squared. All right? And then we recognize that because I have this constant out front, it could be multiplied by this and this, or it will be multiplied by this and this. And because this is an exponential of a sum, that's the same as the product of exponentials. Yeah?
You said minus W, is that supposed to be like minus beta minus W?
So this is minus beta W. Okay? All right. E to the minus beta E is our general form. All right? And so what I've done is I've just brought minus and beta, and I've replaced the energy with this term and that W. Okay? All right, so that means I can write the summation exponential of minus beta W and x squared exponential minus beta W and y squared times exponential minus beta W and z squared. Okay? All right, so all I've done is I've separated this exponential term into 3 individuals, right? Now let's talk a little bit about the summations, right? So if I'm summing through nz, ny and nx are going to be constant, right? We agree with that? Because they're summing through independently of each other, all right? And so really what that means is that I can pull out the others as constants, right? And so the bottom line is that basically means because these are independently summing, these exponentials, this is 3 the product of three summations. Does that make sense? All right, so we can say this is the same as the sum of the e to the minus beta w and x squared sum e to the minus beta w and y squared sum e to the minus beta w and z squared. And we're going from nx equals 1 to infinity, 1 to infinity, 1 to infinity. All right? So we know that this beta is the beta and the w are the same in all three of these, and I'm summing over the same limits. So this summation is the same as this summation is the same as that summation. Does that make sense? Okay? So I'll just write they're equal. And what that really means is all I need to do is come up with an expression for one of these and then cube it. We good? All right, so let me write that out more explicitly. So we'll say that in general, then what I can do is the sum from n equals 1 to infinity of e to the minus beta. All right, so here I'm going to reintroduce the terms. So it'll be n squared h squared over 8ma squared. All right, and then I need to cube it. Okay? All right. So let's take a look at one of the summations. So we'll look at a quick graphical interpretation. So this shows the function, our summation, as a function of n. All right. So if I wanted to say what's the area of the summation, that's going to be the area of the rectangles. So each value of n will give rise to one of these rectangles. All right? And then I have a smooth curve going through here. All right? And for that smooth curve, we see there's a little difference between, I got to find that thing. I feel like throwing it at the wall. It's because I couldn't say the S word. So bad. That's all I'm saying in my head right now. I can't believe it's not spilling out. I'm kidding about that. All right. So at any rate, the area of the rectangles is what is our summation that we're interested in. And if I wanted to use this smooth curve through it, I would choose an integral, right? All right. Now we can do an integral as long as this function is slowly changing with n. So we can, so we'll say the area under the curve equals summation if the function changes slowly with n. All right, and homework 7, number 4 through 7, actually hit this aspect of it and some of the things that follow from this, all right? But one of the questions asks you to calculate the rectangle for n equals 1 and for n equals 2, and then some really large number. And what you see for 1 and 2, it's around 1, each one of them. And then when you get to this big, huge number, it's like 0.8 or 0.9. And that basically says, yeah, it's okay to use the integral. Okay? All right. So that means that we can replace the summation with the integral. And the integral will be from 1 to infinity of e to the minus beta h squared n squared over 8ma squared dn. Okay? All right. And I'm thinking that that's an appropriate place to stop for today. All right.